Welcome to this lecture series in coordinate geometry. We will continue our discussion from last time and finish the thread about equations of lines that we started. All we need to know is some very basic things like what is the meaning of the slope of a line and what is the meaning of the equation of a line. So let me just recall this we discussed extensively. So if we have a line, then you take the angle that is made by the positive direction of the x-axis and the line and take the tan of that angle. That is defined as the slope of the line. So this could be positive, negative, 0 or infinity. Anything is possible. If the slope is infinity, then the line is vertical. If the slope is 0, then the line is horizontal. If the slope is positive, the line looks like this. And if the slope is negative, the line looks like that. Okay. Here are some problems for practice. And now let us get started. So first, let us make a very small comment about slope quickly. So suppose we have a line and we are given 2 points on the line, 2 distinct points. Their coordinates are x1, y1 and x2, y2. So what is the slope of this line? Well, if you just make this triangle, draw a horizontal line passing through the first point and a vertical line passing through the second point, you will see that this is the angle that this line makes with the positive direction of the x-axis, and therefore the slope of this line is the tan of this angle, which is this upon that, but this distance is y2 minus y1 and this distance is x2 minus x1. So I don't want to do this in too much detail. Directly, let me just write that the slope of the line is m, which is given by this formula. Okay, and this works despite or regardless of the fact that this line could be vertical. If the line is vertical, then x2 and x1 would coincide. And since these 2 points are distinct, y1 and y2 would then be different. And hence m would be the ratio of a non-zero number with 0, and by convention we write that as infinity. So that works. And if the line was horizontal, then x2 and x1 would necessarily be different, while y2 and y1 would be equal. So you get 0. So it works, even in those boundary cases. Okay. So now basically the point of this lecture is to see various situations where one can write down explicit formula for the equation of a line. All of these have separate names, but nobody I know would remember them. They have been given names, so that's why I have written it. 2-point form. So this is the form where you are given 2 distinct points that lie on the line, and now we want to write down the equation of the line which passes through these 2 points. Since these are 2 distinct points, there is a unique line that passes through them. So that's that, and now let us try to write down the equation. So it's very simple. The idea is basically just pick a point, let's say this point, call it x comma y. So we will just write down the slope of this line in 2 different ways. We will first use this point and that point to write the slope, and then we may use this point and that point to write the slope. And as usual, one should be careful in the, whenever we have 0 appearing in the denominator, one should be careful. So the calculation that I'm going to make would be under the assumption that x1 and x2 are different. Because otherwise the line is vertical, we will deal with that case separately. Okay, so in that case, what is the slope? If we take a look at these 2 points, the slope would be y minus y1 divided by x minus x1. And if we take a look at these 2 points, then the slope is y2 minus y1 divided by x2 minus x1. Now, the careful reader will notice that this equation is valid only when x comma y is chosen different from this guy. Right? Only then we can write this, because otherwise we will see 0 upon 0. Right? So this is under the assumption that x comma y is different from x1 comma y1. That's fine. So this implies that y minus y1 times x2 minus x1, and it is legitimate to write x2 minus x1 because we have already assumed this. This is equal to y2 minus y1 times x minus x1, which implies, just doing plain algebra, so this cancels out, and I don't think anything else cancels out. So let's collect maybe the coefficients. So we will collect the coefficient of y, we will collect the coefficient of x. Yeah. So this implies this is what we get. And so the equation becomes this is what we get as the final expression. So if x comma y is a point lying on this line, then this must necessarily hold. This was shown under the assumption that this is the case, but even if we take x as x1 and y as y1, let's see what happens. If you take x as x1 and y as y1, then hopefully you should get this, which I have to compute. So you get x1 y2, right, with a minus sign, which is here. You get x2 y1, which is here, and x1 y1 with a negative sign, and x1 y1 with a positive sign, so that cancels out. So this is satisfied even with this, this dropped. Even if we do not assume this, the final equation is satisfied. So regardless of what happens, so far we have assumed this, regardless of what happens, if x comma y is a point on this line, then this equation must be satisfied. And conversely, if this equation is satisfied, then you can just reverse the steps to show that x comma y must lie on this line. This reverse step is generally skipped in textbooks. What textbooks do is they do this direction. They start with a point, they do all this nonsense, they probably don't even write this, I think, and they do all this nonsense, they come to this conclusion and just write down that this is therefore the equation of the line. The answer is correct, but the reasoning is faulty. This only shows one-way implication. This shows that if you assume x comma y is on this line, then this must hold, but the converse has to be shown for it to be a proof. Alright, so that converse direction I leave as an exercise. Now, even if we drop this assumption, let's see what happens. If x1 were equal to x2, then it's very easy to write down the equation of this line straight away. The equation of this line would be just x equals x1, which is equals to x2. And I think that this will still hold under that assumption, because if x1 were equal to x2, this term would just simply vanish. And here you will take the correct thing as common and cancel out, and still this works. So even though we came to this conclusion under this assumption, one can easily check that this conclusion holds regardless. So this is the equation of the line passing through these 2 points, as long as these 2 points are distinct. Okay, so this is called the 2-point form. Again, I don't think anybody makes an effort to remember this. I certainly don't, and I would also not encourage you to remember any of this. What is important is the reasoning. Okay, the slope-intercept form. This is perhaps the most famous form. So suppose you have a line which is not vertical, then it will necessarily intersect the y-axis at some point, and let's say this c is the signed distance of the point of intersection from the origin. So if this point lies above the origin, we'll have a positive intercept, If this point of intersection lies below the origin, we'll have a negative intercept. So this c is not a positive, not necessarily a positive number. It could be a negative number or even 0. Okay, so we have this data given that the intercept is c, and we are also given the slope. So let's say this angle is theta and m is equal to tan theta, which is to say that the slope is m. Then can we write down the equation of this line? Of course we can, because we already know one coordinate. The coordinate, this one, this is 0, c. That's what this coordinate is. And now again, if we choose a point x, y here, it must satisfy the equation. Assuming x, y is different from 0, c, we can say that this equation holds. And also, let's say x is non-zero. So this must be equal to the slope of the line. All we did was, we have this point on the line, that point on the line. So the slope of the line is, as we commented, y2 minus y1 divided by x2 minus x1. Okay, so here these assumptions have to be made in order for us to be able to write this. But then this translates to, or just by doing the algebra, we get y is equal to mx plus c. So if x, y is on this line and different from this point with the additional assumption that x is non-zero, we must necessarily have this. But again, even if you drop these assumptions, if x, y were equal to 0, c, this is still satisfied. And if x equals to 0, this is still satisfied. So we make the deduction that whenever x, y is a point on this line, this must hold. And the converse you can check. If this holds, then x, y must lie on this line. So that converse again I leave as an exercise. And the slope-intercept form suggests or says that if c is the intercept and m is the slope, then the equation of the line is y equals mx plus c. Okay. Point slope form. This is very similar to the previous one. Here we are given a point through which the line passes, and we are also given the slope of the line. And assume that the line is not vertical. So yeah, even in the previous thing, it doesn't make any sense to say if the line were vertical, then either there would be no intercept or the line would coincide with the y-axis. So here it doesn't make any sense to, have the slope as infinity. That case simply doesn't make any sense. But here you could have a vertical line passing through a given point. So that one can deal with separately. So we will make our deductions in this case where the line is not vertical. And it's the same thing. If you pick a point x, y, and now I will be a little bit sloppy, perhaps maybe writing all the proper assumptions is tiring, but I'll try. So if this is the case, different from the point that is given, and so maybe more assumptions will be made, but here is the thing. The slope of the line is this, which is given to be m, and here we will make the assumption that x is not equal to a. So x not equal to a already covers this, so we don't even need to write that. So we get y minus b equals mx minus a, and this is your point slope form. As it happened in the previous thing, even if you drop this assumption, this is still satisfied, and therefore whenever x, y is a point lying on this line, this must be satisfied, and converse is an exercise. So this is the equation for the point slope form. In this special case, m is not infinity. In the case that m is infinity, the answer is immediate. The equation of the line would be x equals a. That would be the equation of the line, and you can sort of recover it from here, because if m is infinity, you divide both sides by m, which is illegitimate. You cannot divide both sides by infinity, but this is just a mnemonic, so to say. So you divide both sides by infinity. On the left side you will get 0, on the right side you get x minus a, and hence x minus a is 0. But this reasoning is not acceptable. The proper reasoning is make two separate cases, that m is not infinity, in which case you can do all this, and separately if m is infinity, then you just straight away write down the equation of the line x equals a, simply because all the points of the line must satisfy this, and if a point satisfies this, it will be on the line. So that's a separate exercise. Okay. Normal form. So just give me 1 second. Yeah, normal form, again, this is very easy. So maybe I'll just do it in a pedestrian way. What is the data given to us? We have a line which is at a distance p from the origin, and this perpendicular line makes an angle of alpha with the positive direction of the x-axis. Okay, and assume that alpha is in this region. You can write down, you can follow similar steps and get an equation even if you do not assume alpha is in this range. But I will make the computation assuming this so that there are no hiccups. So the most obvious approach is pick a point on this line, x, y, and see where it goes. So first of all, since the slope of this line is tan alpha, one can immediately write down the slope of this line, because these two lines are perpendicular and none of them are vertical. Why none of them are vertical? Because this is neither vertical nor horizontal. So its perpendicular line will be neither vertical nor horizontal. And since it is not vertical, that is all that we care about. Since this is not vertical, its slope is not infinity. And therefore, one does not need to worry about any of the steps. So what is the slope of our line? The slope of our line is minus 1 upon tan alpha. Why is that? Because as we saw in the previous lecture, the product of slopes of two perpendicular lines is minus 1, provided none of the lines are vertical, which happens in this case. So this is our slope, and now we just, we figure out what this point is. What is this point? Basic trigonometry says this is the x coordinate is p cos alpha and the y coordinate is p sin alpha. So this is p cos alpha comma p sin alpha. And yeah, if this is the case, assuming this, we have, and assuming that x comma y lies on the line, we have slope computed in two different ways. Right, and if you do the algebra, just plain simple algebra, what have I written? This bracket was supposed to be here, right? In fact, all we need to assume is that x is not equal to p cos alpha. So if you assume x is not equal to p cos alpha and that x comma y is on the line, then this must hold, because we have just written the slope of the line in two different ways. And if you do the algebra, you get y sin alpha plus x cos alpha equals p. And again, as usual, even if you drop this assumption, this must hold. So whenever x comma y is a point on this line, this must hold. And if this holds, then x comma y must lie on this line, which again is an exercise, the converse. So this is the equation for the point slope form. And even if you drop this assumption that holds, maybe you will need to assume, maybe nothing is to be assumed. So if p were 0, still I think this should be fine. Yes, p could be 0 also. Of course, p is a non-negative number. P cannot be negative. Okay, so yeah, I think this is very, very general. You don't need to assume anything about alpha or p, but anyway, the computation that we made was sort of keeping this in mind so that there are no hiccups, but you can figure out the boundary cases. Right, just make 4 different diagrams. If alpha is in the second quadrant or third quadrant or fourth quadrant, just 4 different things, and all the time you will just end up with that. Okay, so that is the normal form. And now for the intercept form. So here we have two non-zero numbers, a and b, and we have a line which cuts the x-axis in the coordinate a. So again, a is a signed number, a could be negative or positive. And similarly, b is the intercept, the y-intercept of the line. B could be negative or positive. But the computations that we will make will be under kind of this assumption that A and B are both positive, but you can make 4 separate cases and see that the same conclusion will hold. So one can do it in a very pedestrian way, just take a point x comma y, write down the slope in 2 different ways, but one can do this in a, shorten the computation. So suppose I have a point x comma y here. What we will do is use similarity of triangles. So we draw a perpendicular on the y-axis and on the x-axis. So this point is x comma 0, or maybe better yet, we just need to record the distances, sorry. So this is x and this is y. Okay, maybe a different color would help. This is confusing me. Very bad. Anyway, so we have this triangle, and just observe that this triangle is similar to the big one, and therefore this length upon that length is same as this length upon that length. And our, the calculations that we will make will be under the assumption that x comma y is such that x and y are both positive and a and b are both positive, and that x comma y lies on this line. So then the similarity of this triangle with that triangle says that y upon b is equal to a minus x upon a. So what happened? This upon that is equal to this upon that, but this is a minus x and this is a. So that's why we get this expression on the right hand side. So this is written under this diagram, and in this diagram we have made all these assumptions, but again you can make several cases and see that you will end up with the same thing, regardless of where x comma y is, as long as it is on the line. So this immediately gives us that x by a plus y by b is equal to 1. So if x comma y lies on this line, this happens, and if this happens, you can show that x comma y lies on this line, just like in the previous cases. So this is the intercept form of the line. Good to remember this. Maybe this one is memorable. Okay. And yeah, that is, no. So there is one more thing, general form. So suppose and not both of a and b are 0. Then this is an equation of a line, or the equation of a line. So how do you show this? Why is such a thing equation of a line? Well, suppose b were non-zero. You can make 2 cases, either a is non-zero or b is non-zero or both. So if b is non-zero, then the equation is equivalent to y equals minus a upon b x minus c upon b. And now you can compare this with the slope-intercept form. So this is the equation of the line whose slope is this and intercept is that. So therefore, this is the equation of a line, and similarly, if b were 0, then it's even easier. If b were 0, then all you have written is ax equals c, which is same as x equals minus c upon a, which is a vertical line. So regardless of that, this is the equation of a line, and every line has such an expression. No matter what line you take, there will exist an A, there will exist a B, and there will exist a C, such that ax plus by plus c equals 0 is the equation of that line. And you can use whichever form of the line you like. You pick two different points on the line, and the 2-point form already gives you such A, such B, and such C. So, long story short, this is the general form of a line. Here it is important to assume that A and B are not both 0, because if both of them were 0, then this is not an equation of a line, because it's not saying anything. It is because then if C is non-zero, then this is bogus, and if C is 0, then every point of the plane would satisfy this, right? If A is 0 and B is 0 and C is also 0, then every point of the plane would satisfy this, and hence this wouldn't be an equation of a line. So the assumption that not both A and B are 0 is important. And yeah, so every line is of this form, and everything of this form is a line. Okay, so that's the general form of a line. And with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.